August 17, 1943. 30,000 feet above southern Germany, the sky over Schweinfurt was alive with fire. Hundreds of black flak bursts blossomed around the tight bomber formations as 230 American B-17 flying fortresses pushed deeper into enemy airspace. Inside the lead aircraft, the bombardier lay flat behind the glass of his Norden bomb sight, adjusting dials with gloved hands, trying to ignore the violent shudder of explosions rocking the plane. Through brief tears in the smoke below, 5 industrial complexes came into view. They did not look extraordinary. Long roofs, rail spurs, chimneys, warehouses. But together, these factories produced nearly 2/3 of Germany's ball bearings, tiny metal components without which modern machinery simply could not function. The German aviation industry alone consumed more than 2 million ball bearings every single month. Tanks, trucks, machine tools, locomotives, turbines, submarines, all depended on them. Allied planners believed that if Schweinfurt was destroyed, the German war machine would seize up like an engine run dry of oil. That was the theory. As the bomb bay doors opened and thousands of pounds of explosives fell toward the factories below, German fighters swarmed in. Messerschmitts and Focke-Wulfs tore through the bomber streams. Tracer fire stitched the sky. Aircraft burned. Crews bailed out. Others vanished in spirals of smoke. By the end of the day, 60 B-17s were gone. Over 600 airmen were missing. More than 100 were dead. While American crews were dying over Bavaria in an attempt to cripple German bearing production, something deeply ironic was happening thousands of miles away, in quiet industrial towns across the United States. American factories were already producing a bearing Germany could not easily replace, could not quickly copy, and could not stop by bombing Schweinfurt. A bearing that worked better for most military applications. A bearing that did not depend on German technology at all. Its story began not in World War II, not in Ohio, and not even in America, but in the mind of a German immigrant carriage maker, working in the late 19th century, obsessed with a deceptively simple problem: friction. Friction is the enemy of motion. Whenever two surfaces move against each other, energy is lost. Motion becomes heat. Metal wears. Efficiency collapses. From the first wagon axle to the most advanced turbine, controlling friction has always been one of engineering's central challenges. Henry Timken believed that anyone who could meaningfully reduce friction would create something of lasting value. He was born on August 16, 1831, in the Kingdom of Hanover, in what is now Germany. When he was 7 years old, his family emigrated to the United States, settling in Missouri. America was young, expanding, and hungry for infrastructure. Wagons, railways, machines, everything was being built, and everything depended on parts that could move reliably under load. As a teenager, Timken apprenticed with a respected wagon and carriage maker. He learned woodworking, metalworking, and, more importantly, the realities of mechanical failure. Axles seized. Wheels wore out. Bearings failed. Every breakdown was a lesson. By his mid-20s, Timken had opened his own carriage factory in St. Louis. He was not just a craftsman, he was an experimenter. In 1877, he patented an improved buggy spring that distributed load more effectively and survived rough roads better than existing designs. The spring was widely adopted across America and produced under license by multiple manufacturers, generating steady royalty income. The success of the spring brought Timken financial security and time. Time to think. By the 1890s, he became increasingly focused on friction in wheel assemblies. Traditional bearings of the era were crude by modern standards. Most wagon wheels relied on plain bearings, simple metal surfaces sliding against each other, lubricated with grease. These worked, but they wasted enormous amounts of energy and wore out quickly under load. Ball bearings, which used hardened steel spheres rolling between two races, were a major improvement. They dramatically reduced friction and were ideal for light loads and high rotational speeds. But Timken noticed a recurring problem. Wagon wheels did not experience simple, straight-down loads. They carried weight vertically, yes, but when a wagon turned, or hit uneven ground, or carried heavy cargo, the wheels experienced side loads and thrust loads at the same time. Ball bearings struggled under these combined forces. Their point contact concentrated stress, causing rapid wear and failure. Timken believed there had to be a better way. With the help of his 2 sons and a nephew, he began experimenting. The solution they developed was elegant and radical. Instead of balls, they used rollers, but not cylindrical ones. The rollers were tapered, shaped like truncated cones, and arranged at precise angles between matching conical races. This geometry meant that loads were distributed along a line of contact instead of a single point. The bearing could handle radial loads and thrust loads simultaneously, exactly what vehicle wheels demanded. On May 1, 1898, Henry Timken was granted patents for the tapered roller bearing. The impact of the invention was profound. Compared to ball bearings of similar size, Timken's design could carry several times the load, run cooler, last longer, and be adjusted as it wore. It transformed the way heavy machinery could be built. In 1899, Timken incorporated the Timken Roller Bearing Axle Company, initially operating from a corner of his existing carriage factory in St. Louis. Demand exploded almost immediately. By 1901, it was clear that the company needed to be closer to America's emerging industrial heartland. Timken relocated operations to Canton, Ohio, strategically positioned near steel suppliers, rail networks, and the growing automotive industry centered in Detroit and Cleveland. While Timken was refining roller bearings in America, Europe, and Germany in particular, dominated ball bearing production. German engineers had pioneered precision steel manufacturing decades earlier. In 1883, Friedrich Fischer developed a machine capable of mass-producing hardened steel balls with unprecedented accuracy. His factory in Schweinfurt became the foundation of what would grow into one of the world's largest bearing conglomerates. Other companies followed. By the early 20th century, German and Swedish manufacturers, most notably SKF, had built global bearing empires. They controlled advanced metallurgy, grinding techniques, and international distribution networks. Before World War I, the majority of ball bearings used in American industry were imported from Germany. Timken himself traveled to Europe in the 1890s, visiting German workshops and observing early internal combustion engines from Daimler and Benz. He understood how far ahead Europe was in precision manufacturing. But he also saw something they did not. European firms were perfecting ball bearings because that was the technology they knew. Timken's tapered roller design addressed a different class of problems: heavy loads, combined forces, durability over speed. By 1920, the Timken company produced roughly 90% of all tapered roller bearings made in the United States. Railroads were early adopters. Tests on streetcars and freight wagons demonstrated dramatic reductions in maintenance and fuel consumption. High-speed passenger trains soon followed. Locomotives equipped with Timken bearings ran faster, farther, and cooler. The technology spread quietly, steadily, without headlines. When World War I erupted in 1914, Germany's dominance in ball bearing production suddenly became a strategic vulnerability for everyone else. The British naval blockade cut off German exports. American manufacturers dependent on imported bearings faced shortages and soaring prices. Replacing ball bearings was not easy. Precision ball production required specialized machinery and skills concentrated almost entirely in Germany. Timken, however, was in a different position. Its factories already produced a bearing that could replace ball bearings in most heavy applications, and often outperform them. Trucks, artillery, rail equipment, and industrial machinery all transitioned to tapered rollers with minimal redesign. The war revealed something critical. Dependence on a single foreign technology could cripple an entire industrial economy. Timken learned another lesson as well. Control of materials mattered as much as design. In 1917, facing steel shortages and inconsistent quality, the company began producing its own bearing steel in Canton. Vertical integration allowed complete control over chemistry, heat treatment, and cleanliness, factors absolutely essential for bearing reliability. This decision would echo through history. Henry Timken did not live to see the full impact of his invention. He died in 1909. But his sons carried the company forward, expanding production, entering global markets, and quietly embedding tapered roller bearings into the backbone of modern industry. By the 1930s, Timken was one of America's most stable industrial firms, diversified across rail, automotive, agriculture, machine tools, and heavy equipment. When the world slid toward war again, the company was ready. By 1943, Allied strategists believed that Germany's ball bearing industry was the Achilles heel of the Reich. Intelligence reports identified Schweinfurt as the critical node. What they did not fully appreciate was that Germany's enemies were not equally vulnerable. When the bombs fell on Schweinfurt, German production was damaged, but not destroyed. Stockpiles cushioned the blow. Imports from neutral countries continued. Engineers substituted simpler bearings where possible. Production dispersed. Meanwhile, American war production surged without interruption. Timken plants ran day and night. New facilities opened across Ohio. The company produced bearings for nearly every piece of Allied equipment. Every Jeep used 24 Timken bearings. Hundreds of thousands of Jeeps rolled off assembly lines. Trucks, tanks, artillery, aircraft landing gear, ship propeller shafts, all depended on bearings that could survive shock, dirt, overload, and neglect. Tapered roller bearings did exactly that. They carried more load. They lasted longer. They could be adjusted instead of replaced. And they were made entirely within the United States, from steel to finished product. While Germany scrambled to protect centralized ball bearing plants, America quietly solved the problem by not needing them. The physics behind that advantage were simple, but devastatingly effective. A ball bearing touches its race at a point. Under load, that point deforms slightly into a tiny oval, but the contact area remains extremely small. Stress concentrates intensely at that spot. Under heavy combined loads, only a few balls carry most of the force, accelerating fatigue and failure. A tapered roller bearing works differently. Each roller contacts its race along a line. Under load, that line spreads into a narrow rectangle, dramatically increasing contact area. Stress is distributed instead of concentrated. All rollers share the load more evenly because of the bearing's geometry. Heat dissipates faster. Wear slows. Service life extends. For high-speed, light-load applications, electric motors, instruments, machine tools, ball bearings remained ideal. But for military vehicles grinding through mud, shock, and neglect, tapered rollers were superior. German engineers understood this in theory. But theory does not win wars. By the time World War II began, Germany's bearing industry was deeply invested in ball bearing production. Retooling factories, retraining workers, redesigning equipment, all of it would have required time Germany did not have. War freezes technology in place. You fight with what you already make. America, by contrast, entered the war with dispersed, vertically integrated bearing production built around tapered rollers. The difference would never appear on a battlefield map. But it would shape every battlefield outcome. After the disastrous Schweinfurt raids of 1943, Allied bombing strategy shifted. Long-range fighter escorts were still unavailable. Loss rates were unsustainable. The ball-bearing campaign faded into history as one of the most costly air offensives with the least decisive results. German armaments minister Albert Speer later admitted that concentrated attacks might have crippled production, but only if sustained. They were not. Germany adapted. Underground facilities replaced centralized factories. Imports filled gaps. Stockpiles grew. By 1945, Germany actually held more bearing inventory than before the raids began. The airmen paid the price anyway. But the outcome of the war did not hinge on Schweinfurt. It hinged on logistics. And logistics hinge on components that almost no one notices, until they fail. During the war years, Timken's output more than doubled its previous peak. The company manufactured hundreds of millions of bearings. Its factories produced gun tubes, rock bits, steel tubing, and precision components that fed every branch of the Allied war machine. The Timken Ordnance Company alone produced tens of thousands of artillery barrels. New plants opened in Zanesville, Columbus, Newton Falls. Employment surged. Production never stopped. Every bearing that did not fail meant one less vehicle sidelined. One less repair crew diverted. One more convoy that reached the front. The advantage compounded invisibly. German industry fought the war with chronic bearing anxiety. American industry barely thought about it. That contrast mattered. After the war, American machinery flooded Europe under the Marshall Plan. Tractors, locomotives, factory equipment, much of it fitted with Timken bearings. European industries rebuilt using American components, not because of ideology, but because they worked. Ironically, this success created legal trouble. In the post-war years, the US government pursued antitrust cases against American firms with international agreements. Timken was accused of restraining trade through territorial arrangements with its British and French affiliates, agreements originally designed to manage capacity during wartime shortages. The Supreme Court ruled against Timken in 1951. The company restructured its international operations and moved on. The growth did not slow. By the 1960s and 1970s, Timken operated on every continent. It entered Japan, one of the world's most demanding bearing markets. It expanded across Europe, Asia, South America, and Africa. In 2003, Timken acquired Torrington, doubling its size and securing its position as a global leader. In 2014, bearing and steel operations separated, allowing each business to focus independently. By the 21st century, Timken employed tens of thousands of people and generated billions in annual revenue. It manufactured not only tapered rollers, but ball bearings, spherical bearings, cylindrical bearings, thrust bearings, and precision systems for aerospace and industry. Yet tapered roller bearings remained its foundation. From bearings small enough to fit inside computer drives to custom units weighing several tons for steel mills and wind turbines, the same geometry patented in 1898 remained central. The physics had not changed. The final irony of the story is this. Henry Timken was German by birth. He learned precision from German craftsmanship. He studied European engineering firsthand. But it was in America that his idea flourished. Not because it was flashy, or dramatic, or politically favored, but because American industry could adopt it at scale. Germany entered World War II dependent on centralized ball bearing production vulnerable to bombing and blockade. America entered the war with diversified bearing technology, domestic steel production, and a design better suited to the realities of military machinery. No general ever gave a speech about bearings. No medal was awarded for reducing friction. But armies do not move on speeches. They move on axles. And axles move on bearings. While bombers burned over Bavaria trying to destroy German factories, American plants in Ohio quietly produced something better. Not through daring raids or grand strategy, but through patient engineering and relentless manufacturing. The bearing war was not won in the sky. It was won on factory floors, where an immigrant carriage maker's idea rolled off production lines by the millions. Henry Timken never set out to influence global conflict. He wanted to build a better wagon. In doing so, he solved a problem that generals could not, and helped ensure that when the greatest war in history came, American machines kept moving. Friction was reduced. Motion continued. And victory followed.